Hello and welcome to our lesson on solving radical equations. So we've talked about simplifying expressions, we even have talked about our radical functions, and this would be the last topic in this module, and that's solving equations. So we know the difference. We know expressions don't have equal signs, we just simplify. We know functions do have equal signs, but on opposite sides of those equal signs we have two different variables, and the relationship between two variables can be graphed. Now if we're solving an equation, there's still going to be an equal sign like with the function, but there's only going to be one variable in the equation that we're trying to solve for. So first, what does it mean for the equation that we're solving to be a radical equation? For instance, is this an example of a radical equation? Is radical 5 plus x equals 1, is that a radical equation? How about this one? X minus x radical 3 equals 6. And how about this one? Radical 2x minus 1 equals 5. Well, of those three, only one is technically a radical equation. In order for our equation to be considered a radical equation, the variable has to be underneath the radical. So it's an equation in which the variable is underneath the radical. So this is not a radical, the first one here is not a radical equation because this is just some decimal amount that we could subtract over. This is a linear equation. And then here, same thing, this is just some decimal amount, like 1.7. Well, I could take 1 minus 1.7x, combine those like terms, and then solve for x, right? This is, again, just a linear equation. The only one of these that is a radical equation is this guy, because here our variable is underneath the radical. So this is, this is a no, not a radical equation. This one is not a radical equation either. And this last one is the only one, again, of the three that is. So this is an example of a radical equation. Okay, so the good news is that solving a radical equation is just like solving a linear equation, where the goal is to get x by itself. So let me show you some examples here. If we were solving this first one, which is, again, just a linear equation, we would solve by getting x alone. So our first step in getting x alone would be to subtract 3 from both sides. That would leave us 3x equal to 15 minus 3 would be 12. Then we would divide both sides by 3. That cancels the multiplication, and so x would be equal to 4. No big deal, okay? The next one is an example of a radical equation because now the x is underneath the radical, but we would solve exactly the same way. So instead of focusing on getting x by itself, we're going to focus on getting radical x by itself. So we would still begin this by subtracting 3 from both sides. So then we would have a radical x equal to 12. We would still then divide both sides by 3, and then that would leave us a radical x equal to 4. Now here we are done because x is all by itself. On the second example here, we have the radical x by itself, but we need x to be all by itself for this to be solved. So we have one extra step to take here. Once the radical is by itself, how do we get rid of it? Well, the opposite of, let's see here, plus 3 and minus 3, the opposite of times 3 was divide 3. What is the opposite of the square root? Well, that's going to be squaring. So what we need to do to get rid of the square root at this step is to square both sides. So we're going to square, I thought I said green. We're going to square this side, we're going to square this side. The square and the square root are opposites, they cancel. So then x comes down all by itself, which is what we wanted. And then on the other side, 4 squared gives us an answer of 16. So 16 is going to be our solution here. And then remember, we can always check, right? If we plugged 16 back in here for x, we would take the square root of 16 to get 4, we would multiply by 3 to get 12, and then we would add 3 to get 15, which is what we wanted to happen. Okay, so that's the gist. I just wanted to show you one other example. If you compare, if we compare the second one here to the third one here, I just moved the radical, extended the radical a little bit, so that the plus 3 was no longer outside of the radical. In this last one, it's in the radical, and that makes a difference. The plus 3 underneath the radical is not just a plus 3 on that side of the equation. So I cannot start by subtracting 3 like I did in the previous two equations. That plus 3 is trapped in the radical. It can't be moved until the radical is gone. And we're not going to get rid of the radical until everything outside of it is gone. So just like we started here by getting the radical by itself, we're going to start in this problem by getting the radical by itself. So if our radical is being multiplied by 3, we're going to divide both sides by 3. That would leave us the radical x plus 3 equal to 5. Again, that plus 3 is underneath the square root. I cannot move it until the square root is gone. It would be like being trapped in parentheses. It's trapped in there, okay? So our next step is going to be to get rid of that square root by squaring. So we're going to square both sides. Again, the square and the square root are going to cancel. So our entire radicand, which was x plus 3, can come down now without the square root. And then on the other side, 5 squared makes 25. Now that the radical is gone, we're going to take an extra step to get rid of this plus 3. Now we can subtract it over, and that gives us our final answer, which is 22. Okay? So the goal is, like when we solve a linear equation, when we're trying to get x by itself, the goal is to get the radical by itself. So get the radical by itself. That means anything that's being added or multiplied or subtracted, we would move those things over using inverse operations. And then once the radical is alone, we will get rid of the radical. If it's a square root, we're going to square like we did here. If it was a cube root, we'd have to cube both sides. If it was a fourth root, we'd have to raise both sides to the fourth power, and so on. So we'll get rid of the radical by raising both sides to the power that's going to be necessary. And then sometimes we're done, like here. In the second example, we squared both sides and we were done. But sometimes after we square both sides, like here in the third one, we squared both sides, we still might have to get x by itself. But we can use inverse operations to do that as well. Okay? So we want to isolate the radical as our first step. We're going to get radical x minus 1, whatever it is. Get the radical all by itself, just like we would try to get x all by itself. Then we're going to get rid of the radical. And we do that by raising both sides of the equation to the power of the index. If it's a square root, index is 2, we square both sides. If it's a cube root, the index is 3, we cube both sides. If it's a fourth root, the index is 4, we fourth both sides. Now, raise both sides to the fourth power, okay? And then if necessary, then we will continue to solve for x. And we got to be careful with radical equations. Not all radical, I mean, we want to be careful when we're solving in general, but we really have to be careful when our radical equations have even roots. Anytime there is a restriction for our equation, there's this possibility of getting extraneous solutions. If you remember, in our rational unit, if we had an equation like 1 over x plus 3 equal to, let's say, 1 over x minus 4, we had two restricted values for this equation. We said x could not be a negative 3, because a negative 3 and positive 3 would make this denominator equal 0, which was no good. Okay, and we said x could not be a positive 4, because if I put a positive 4 into this denominator, 4 minus 4 again would make 0 in the bottom. That's no good. It's undefined. Okay, so anytime there's a restriction, we have the possibility of having this extraneous solution, where remember we could solve and get one of those restrictions as a solution, but it couldn't work because it's undefined when we plug it back in. So we have restrictions with fractions. Fractions can't have denominators equal to 0. And we also have restrictions with even roots. Remember, for a square root, I can't, for example, take a square root of a negative 4 and get a real number answer or solution for that. So anytime we're restricted, we have, again, this possibility of getting extraneous solutions. So radical equations with even roots, these are the ones we have to worry about. Cube roots, fifth roots, those are not restricted. We can take odd roots of any types of numbers, so we won't get extraneous solutions there. But if we have an even root, we have the possibility of having an extraneous solution. And those, remember, don't count as valid solutions. So we want to be extra careful with our radical equations that have even roots. All right. So let's look here at number 1. We want to get the radical by itself. So our first step is going to be to add 1 to both sides. That's going to leave us with 3 radical x equal to 6. Now I want to divide both sides by 3 so that I've gotten my radical x all by itself equal to 6 divided by 3 makes 2. Once the radical is alone, we get rid of it. Since this is a square root, we're going to square both sides. The square and the square root cancel, leaving me x on the left, and then 2 squared makes 4, my solution. And it's really easy to check. You can do this in your head, but I'll just show you on paper here. If you plug the 4 back in, this is going to be a true statement that's left. So the square root of 4 is 2, so this is 3 times 2 minus 1. 3 times 2 is 6, and 6 minus 1 is absolutely 5. So it all checks out. We get a true statement there. And if you didn't want to do that by hand or in your head, you could use the calculator to do that as well. Okay? So it definitely works. Let's try another one here, where we have got, again, the same numbers, but now the 3 and the 1 are underneath the radical. So I cannot move the 1 or the 3 in the same way I did in the first problem. This one, the radical is all by itself. There's nothing outside of it that needs to be moved. So we're going to start this one by getting rid of the radical. We are going to start by squaring both sides. That's going to cancel the square root here and bring down the radicand, which is just the 3x minus 1. And then on the other side, 5 squared makes 25. Now that the radical is gone, I can get rid of my minus 1. So I'm going to add to both sides. And 3x is equal to 26. And now I can get rid of the 3. So I divide both sides by 3. And then we have it. X equal to, this doesn't divide or reduce. So 26 thirds is going to be our answer. Maybe not as nice to check, but we could plug it in and check, right? If we did 3 times 26 over 3 minus 1 under the radical, it should equal 5. These 3's will cancel. 26 minus 1 is 25, and the square root of 25 is, in fact, 5. So this one checks out as well. Okay? Alright, moving right along. Let's see. Alright, here we go. Number 3. Again, we want to get the radical by itself. So the first thing we're going to move in this one is this positive 2. We're going to get rid of the positive 2 by subtracting it from both sides. So subtract 2, subtract 2. That's going to leave me 5 times the square root of x minus 4 equal to a 10. Now I want to get rid of 5 times by dividing both sides by 5 to get my radical all by itself. So now my square root of x minus 4 is all alone equal to 10 divided by 5 on the right there is going to give us a 2. Now that the radical is alone, we can get rid of it. And we get rid of a square root by squaring both sides. The square and the square root will cancel, leaving us an x minus 4. And on the other side, 2 squared gives us a 4 again. And now here we can take an extra step. We got the radical by itself, we got rid of the radical, but x still isn't alone. So now that the radical is gone, we can move this negative 4 by adding it to both sides. And finally our answer, x equals 8. Okay, and again we can check this. And you can feel free to do this in your head. I just want to show you what should be happening in your head. When you plug in the 8 minus 4 under the radical is going to give you 4, and the square root of 4 is going to give you 2. So 5 times 2 is 10, and then 10 plus the 2 gives you 12, which is in fact what we wanted to get. So that solution checks out. Okay? Alright, do we have a U-try? Feels like it's time. Oh yeah, look at that. It's like I made this note sheet or something. Sorry. I've got to keep myself entertained. It's very lonely over here. Alright, so one for you to try if you're feeling confident with this. This is a good spot for you to pause the video and give this a shot. Otherwise, let's see. We want to get the radical alone. So I'm going to get rid of this 5 over here by subtracting it. It's a positive 5, so I'll subtract. So I have this negative square root of x plus 1 equal to 7 minus 5 is 2. Now this 1 is like a negative 1 being multiplied by our radical. So we want to divide both sides by a negative 1 to cancel that. And now my radical is all by itself equal to 2 divided by negative 1 is going to make a negative 2. Sorry, this 2 is really ugly. It was wonky looking. Okay, so now that the radical is alone, we can get rid of it. We get rid of a square root by squaring both sides. Square and the square root cancel, leaving me my radicand, x plus 1. And on the other side, a negative 2 squared. Be careful. We're squaring the entire side, right? So I should be a little more careful here. When we square this side, we want to make sure we're squaring the negative 2. So a negative 2 times a negative 2 means we should be looking at a positive 4 here. And I want blue. So this looks right. All right. Now we can get rid of the plus 1. So we subtract it over, and that gives us an answer of 3, x equal to 3. So let's go ahead and check to make sure this works. If I go to check this, 5 minus the square root of 3 plus 1 should equal 7. Well, 3 plus 1 is 4, and the square root of 4 is 2, and 5 minus 2 is 3, which is not equal to the 7 that we've got there. So it's possible that a mistake was made, but I didn't make a mistake in this one. It happens, right? Sometimes you'll plug it in and not get the same thing and think, oh, it's extraneous, okay? But that's not the case. It's possible that a mistake was made, but I just happen to know that I didn't make a mistake here. I know I planted this problem on purpose. This is an example of an extraneous solution. When I plug this in, it doesn't work, and not because I made a mistake, but because it creates an issue, or there's an issue with the original equation. So this is an extraneous solution. So if the only solution we got doesn't work, that means there is no solution to this equation. Sometimes you're going to get two solutions, and one will work and one won't. Sometimes you get one solution that doesn't work, so you don't have a solution. Now, I would argue that this is one that you should have recognized a little sooner than the end here, that this wasn't going to work out. And that is in this step right here. So right there, when it says that the square root of x plus 1 is equal to a negative 2, is that going to be possible? Can I ever take the square root of something and get a negative result? If I take the square root of 25, I get 5, right? If I take the square root of negative 25, oh wait, I can't do that, okay? I can't square root something and get a negative result. So right here in this step that I highlighted, I know that this isn't going to work. Now, if you recognize it there, you can go ahead and stop and say there is no solution. But if you're not going to see it, then you have to make sure that you're checking your answers. You can kind of also see it up here. You have 5, and you have to take something away to make it 7. And whatever you're taking away, this thing that you're taking away is going to have to be positive, and 5 minus some positive number can't get you to 7. So if you recognized it there, that's fine too, but the reason this one ends up not working is because square roots can't be negative. So if you have isolated a square root or an even root, let's change that. If you have isolated an even root, like we isolated the square root here, and it's equal to a negative, there's no way it's going to work. Even roots can't be negative. Okay, so there will be cases like this one where you can kind of tell it's going to be a no solution problem, or there's going to be an extraneous solution if you continue to solve. Sometimes you won't, and I'll show you one of those as well. Alright, so let's look at this one. We're finally introducing some other indices here. So we've got a cube root, but it works the same way. We're going to get that cube root by itself by dividing both sides by 2. That gives me the cube root of x minus 3 equal to 2 divided by 2 is 1. So now that my radical is alone, I want to get rid of it, but this time it's a cube root. So I get rid of a cube root by cubing both sides. So the cube and the cube root will cancel, leaving my radicand, which is x minus 3. And then on the right, 1 cubed is still 1. Now I can get rid of that minus 3 by adding it over. So adding it over, I end up with x equals 4. And we can check it. We don't have to worry about it being extraneous because it's a cube root, which is unrestricted, but it's still a good idea to check your work, and it's easy, and this can be done in your head again. So 4 minus 3 is 1, and the cube root of 1 is 1, and 1 times 2 is 2, which was exactly what we had on that side of the equation. So we're good. This one checks out. Alright. Next, maybe this looks a little intimidating because we've got square roots on both sides. Maybe not, because both of them are not square roots. We've got fifth roots on both sides. I meant to say we had radicals on both sides, but both of them are alone. So we can go ahead and just raise both sides to the fifth power. That's how we would get rid of a fifth root. Raise both sides to the fifth power, and both of them cancel. So then the radicand on this side has to equal the radicand on the other side, which should make sense, right? If I've got the fifth root of something on the left and the fifth root of something on the right, don't those somethings have to be the same? Yes. So let's get our like terms together here. I'm going to subtract 5x from both sides. That's going to get me negative 2x plus 4 equal to negative 6. Now I'm going to subtract the 4 over. That leaves me negative 2x equal to negative 10. And now my final step is to divide both sides by negative 2. And so at last, x equals 5. Again, we don't have to worry about an extraneous solution here because it is a fifth root, but we can check. If I put a 5 here, that's 15 plus 4, which is 19, so I get a fifth root of 19 on that side. If I put a 5 here, it's going to be 25 minus 6, which is a fifth root of 19 on the other side. So it checks out. Right, good to check your work just to make sure you're doing it correctly. But again, we don't have to worry about extraneous solutions with those odd roots. All right. So this problem is going to be probably, let me just scan real quick, the most challenging, yeah, this will be the most challenging one that we look at. And there's something a little different about it. Can you see what's different about this equation compared to all of the others? Well, this one has a variable underneath the radical and it has a variable outside of the radical, which is going to create a challenge when we solve, and you'll see it in a second, but we still want to follow the same steps. So we want to get our radical by itself, which it is, which means we can move on to getting rid of the square root here. So let's square both sides. But again, we're squaring the whole side, okay? So on the left, non-issue. Square and square root cancel, leaving us 6x plus 13. But on the right, squaring 2x plus 1 means I have to multiply it by itself, okay? So now I have 6x plus 13 equal to a 4x squared, a 2x, another 2x, and then a plus 1. And you can see the resulting equation is going to be quadratic, so we're going to solve different than we would solve a linear equation, which is what we had left in all the others. So quadratic, we're going to solve by factoring for now. So we want to get everything on one side and equal to 0. So I'm going to subtract over the 6x's and subtract over the 13 to cancel these guys out. So 0 is going to be equal to 4x squared comes down. If I put these like terms all together, 2 and 2 is 4, and 4 minus the 6 is going to give me negative 2x's in the middle. And then the 1 minus the 13 puts a negative 12 here. So we're almost, we're actually ready to factor now, but before we use bottoms up, we got to take out our GCF. Hopefully you're recognizing these terms all have a 2 in common. So 2x squared minus x minus 6 is what we're going to try to factor using bottoms up. So 2 times negative 6 is negative 12. Factors that are going to make negative 1 will be negative 4, positive 3. We're going to divide those both by 2, and so this is going to become 2 times 1x minus 2 and 2x plus 3. And then we're going to get two solutions. One of our solutions will be the positive 2 that cancels the negative 2 in that first binomial. And the other solution is going to be a negative 3 halves. We'd have to subtract the 3 and divide the 2. So negative 3 halves is a second solution. So this, obviously a lot more work than all of the others. That's going to happen when you have variables inside and outside of the radical. But this is one of the cases where you just have to verify the answers. There's no way to know that both of these work or one works and one doesn't without actually plugging in to check. And so we have to verify both, okay? So we're going to do this with the calculator. Haven't done one with the calculator yet. So I'm going to put in my square root of 6 times, what was the first solution? 2. 6 times 2, and then plus 13. That plus 13 needs to be out of the radical. Nope, just kidding. Plus 13 needs to be in the radical. Okay, so we get 5 on that side, and then we got 2 times 2 plus 1 which is 5 on the other side. So that works out. Now I'm going to go in here and replace the 2 with a negative 3 halves. So negative 3 halves. And it gets me a 2 on that side. And again, let me replace this 2 with a negative 3 halves. And I get a negative 2 on the other side. So the positive 2 on the one side does not equal the negative 2 on the other side, which means negative 3 halves is not going to work. So this solution is extraneous, but the other solution is valid. So we've got two solutions. One doesn't work, but the one does. So we're just going to go with the one valid solution, the one that checked out. Okay? Alright, so that's about as bad as it can be. Actually, they could get worse. Sometimes you square both sides and you create another radical. It can be worse than this, but I think that's as far as we need to take it. Okay? Alright, let's look at number 7, which again looks a little different, but it does still belong in this section. If you recall, when we have a rational exponent, we can rewrite it in radical form. This is the same thing as the cube root of 2x plus 1 to the first power. Remember, we can read these this way. So if we had like x to the 1/3, cube root of x to the first, okay? Same thing here. We can rewrite this. Even though it looks a little strange, this is the same thing as the cube root of 2x plus 1 to the first power, okay? So what do we have to do to solve this equation? Well, that radical is all by itself, so we can cube both sides. Cube both sides. And really, if we're trying to make an exponent of 1 here, if you have a 1/3 and you want to make it a 1, you'd multiply by 3 over 1. So cubing both sides at that first step would be perfectly acceptable. So if you can see that 1/3 and recognize that you just need to cube here and cube here, totally fine as well. Totally fine to do that. It's just if you want to see it in radical form so that's a little more visual for you, either way is going to work, whatever you're comfortable with. Okay? So we cube both sides here. Those cube and cube roots cancel, so the radicand, 2x plus 1, comes down. And I know it was in parentheses to the first power, but that doesn't do anything, so I'm going to get rid of it. And on the other side, we have a negative 5 cubed. So technically it's in parentheses, but it doesn't matter. Negative 5, negative 5, negative 5, either way, is going to give us a negative 125. Now I want to get x by itself, so subtract 1 over. And now I have 2x equal to negative 126. Lastly, divide both sides by 2. So x is going to be equal to a negative 63. You can check it. It's going to work. You don't have to worry about a restriction here anyway because it's a cube root. Alright, how about this guy? This is probably the most commonly missed type of problem I would see on a practice assignment or a quiz. Most of you are probably recognizing the 1/2 power as the square root, but be careful that 1/2 power, it only applies to the x, not to the 3, right? This is 3 times x to the 1/2. That's what that says. So it should be 3 times the square root of x. So make sure that 3 does not go into the radical. If the 3 was to go into the radical, it would have to be like that, where the 1/2 applies to the 3 and the x. So this is 3 times the square root of x, where your little invisible index of 2 and power of 1 are hiding, okay? And then we still have this minus 2 and then equal to 7. So we want to get that square root by itself. We're going to add 2 to both sides. That gives me 3 times my square root of x equal to 9. Now I can get rid of the 3. So divide both sides by 3. That gives me square root of x equal to 3. Now I can get rid of the square root. And to do so, we square both sides. So square and square root cancel, leaving me x, and 3 squared gives me 9 as my solution here. And if I check it, the square root of 9 is 3, times 3 is 9, minus 2, takes me back to 7. So this one checks out. Okay? One last guy for you to try. If you're confident, give it a shot. If not, let's see. This is the same as the 4th root of x to the first. And then we have a plus 5 and equal to 3. So we're going to subtract the 5 to get the radical by itself. And that leaves me with a 4th root of x equal to a negative 2. If I was solving this, I would stop here. I know that I cannot take the fourth root of something and get a negative. So I can continue to solve, but I know the solution that I get is going to be extraneous. So I would stop here. But if for some reason you had to find the extraneous solution, or if you just didn't recognize that that was happening here, let's go ahead and raise both sides to the fourth power to get rid of the fourth root. That's going to give me x equal to, remember this was in parentheses here, we're squaring the side, so a negative 2 to the fourth power would make a positive 16. But if I go to plug that 16 in, the fourth root of 16 is going to be 2, and then 2 plus the 5 is not going to get us to the 3 that we have there. There's just no way this is going to work, right? There's no way you can take the fourth root of something and get a negative to add to 5 to decrease it to 3. It's just, it can't happen. There's no way this is going to work. So this is an extraneous solution. So again, we only got one solution here, and it doesn't work, which means this equation has no real solutions. There's no soul. Okay? So there it is. We've got some problems to work on the practice. Hopefully they aren't too bad. One of the problems on the practice you're going to see is a pretty ugly looking equation, but I purposely made it multiple choice. So let me just point out, okay? Let me go back to number 6 here, okay? Let's say, let's say number 6 was sitting on your practice or your quiz, and I made it multiple choice. And in the multiple choice answers, I said x is equal to 2, x is equal to negative 3 halves, x is equal to 2 and negative 3 halves, or there was no solution. Okay? You could absolutely go through all of the work and figure out which one of those applies. But in the end, you're going to get both of these as answers, and what do you have to do with them? Well, you've got to plug them back in to check them anyway, right? So if this question was multiple choice, I would not go through the solving work because I'm going to have to check these anyway. So if you had a multiple choice equation, radical equation, and it's a complicated one to solve like this one is, then just take the choices and plug them in. If you're going to plug the 2 in, and you're going to find that the 2 works, so you would maybe circle A so far, but because that's also in C, you're going to have to check the negative 3 halves, and you're going to find out that that doesn't work. So we would eliminate this and this as an option, and obviously because 2 is a solution, it doesn't have no solution. So if the question is multiple choice, work smarter, not harder. Okay? Alright, so I think I've given you plenty of food for thought, but as always, if you need some extra help, just reach out. Alright guys, take care.